This next tutorial will cover how to measure basic distances using the Spatial Analyst toolbar. In the Spatial Analyst toolbar, you'll notice there's a category of distance. Cost and path distance are a little bit more complicated, and they involve using environmental settings and impedances, right, like road networks or other costs to determine how we move through space. But when we want to just measure moving through space unadulterated, or to use the adage, as the crow flies, you use Euclidean allocation, direction, or distance. So for those still grappling to understand raster, this tool is very similar to the vector equivalent buffer in that it measures distance outward in a radius, unimpeded by anything, which is why it tends to be called as the crow flies. So let's engage Euclidean distance. Oh, excuse me, before I even do that, just so that we're using consistency, we're going into our data frame. We are clipping the shape of the data frame to land use. Remember the result of doing that, if I engage, where's my vector land use? It's my raster. If I engage the vector land use, it's simply saying any raster cells or any layer that you create, even if it is larger than this extent, you're containing all of the values visually inside of it. Just helps manage your data. Okay, so back to Euclidean distance. I drag in one rack. That is the thing from which I am measuring my distance. In this case, it's just one bike rack in the center of East Falls. A maximum distance, if I want the values not to exceed a certain distance, I would enter it here. We're going to let it go forever. The cell size should default to 20 automatically. And we don't need to create a direction raster because we're going to do that independently in a moment. So I hit OK. I get what appears to be kind of like a popsicle color. I have some ability with stretched to mess with how the symbology looks. The only big difference I'm going to make is setting this bottom one to 0, just so that we can clearly see the cell from which everything originated. Okay, you can see that tiny little dot there. If I zoom in, that is my origin cell. And let's review how this tool works. So if I get Pixel Inspector, I engage distance 2. Distance is always going to begin, as it should, with 0. So notice the black cell is 0. Now, if I go directly east to the right, it would be 20. If I go down, it would be 20. Notice that those values are exactly the same as the cell size. And that is how this tool works when it's measuring in a straight line. We'll cover how it measures diagonally in a moment. I'm going to engage the drawing toolbar for just a moment so that we can see this a little bit more visually. This is an experiment, so perhaps I will regret this. Very clean, Shay, very clean. All right. Okay, excellent. So I am beginning in this cell right here. This would be cell 0, the equivalent of this black cell here. If I want to measure my distance to this cell, the way the Euclidean distance works is it measures from midpoint to midpoint. Okay, midpoint to midpoint. So if my cell happens to be 20 feet long, because that's the resolution, 20 by 20, then the midpoint to the edge would be half of that, or 10. And then the edge to the next midpoint would be 10, and 10 plus 10 is 20. So even though the cells are measuring from midpoint to midpoint, sometimes it is easier to think about it just as it's measuring in terms of increasing cells, right? So one cell away would be 20, because that's the cell size. 2, 40, because that's 2. 60, 80. And as we continue in these straight lines, that's accurate. 20, 40, 60, 80, so on and so on and so on. 20, 40, 60, 80. Notice that that is not true when going diagonally. The reason that is because the cell is always trying to find the minimum distance needed to get somewhere, right? So to get straight ahead, all it needs to do is go down one cell. To get to the right, it would need to go to the right one cell. To get here, it has three options, right? 1, 2, that would be 40. 1, 2, that would also be 40. Or it could go from this midpoint to this midpoint. But that distance would be slightly larger. Previously, it only had to go from midpoint to midpoint. Or if it went the other way, from midpoint, midpoint. I'm being as accurate as I can here. But now it needs to go a little bit farther if it's going diagonally. It needs to go from midpoint to midpoint. So you can visually see that this is a little bit longer. To calculate how much longer, think about it in terms of a triangle. I'm going to take this one away for a moment. If this took 20, right, the size of a cell, and this took 20, you have a right angle here, and you can use the Pythagorean Theorem. A squared plus b squared equals c squared. So a squared is 20, 20 squared is 400, plus 400 is 800. Therefore, this would be the square root of 800, would be what you would need to do to get from midpoint to midpoint, and that tends to be 28.28. And that's how you measure whenever you're going diagonally. So again, if I were to go down 20 and then this, right? So again, I went down, directly down, and then I went diagonal, it would be 20 plus 28.28, or 48.28. So play around with your pixel inspector, take a look at these, and you'll see that what I'm saying is not crazy, that it's measuring the minimum distance that it would need to get back to this point, that it's very easy because it just increases by the cell size whenever you're moving up, down, left, or right, and whenever you go across the diagonal, it's measuring the square root of the sum of the cell sizes squared, right? So 20 squared plus 20 squared is 800, and the square root of 800 would be the distance going from center to center if you're going on a diagonal. The last thing to keep in mind, the way you interpret this data, let me just open that up real quick. So there's two ways to interpret this data. You could take a look and say this point right here is this far away from any of these points. Or you could say any of these points are that far away from where this is, right? So here, this area of space, because there's not necessarily an object, is defined by being 2,532 feet away. This area of space is defined as being 1,700 feet away, and this area of space is designed as being 1,843 feet away.